So our main focus this week in lectures 6 and 7 is to investigate the orientation of a rigid body and to describe how the orientation changes as the dynamics of the rigid body steps in. So our goal ultimately is to study a rigid body, for example, in space, and here is a video which I will let you see for some time and then we will talk about it. So what you see is something which is tumbling in space, and here is a slow motion of a similar thing, a similar object in space. It is in the space station, so no outside forces or torque are acting on it, and you see that it is executing a ridiculously complex motion. And one of the goals of this course is you should be able to explain that on the basis of dynamics. Okay. So what I have done on the right side is I have taken snapshots of this video at various stages. You may have seen that there are arrows attached to the body. These are the body fixed coordinate system. So it's a coordinate system which is rigidly attached to the rigid body, fixed to the rigid body, so it moves and tumbles and basically stays with the rigid body. So let's have a look at several snapshots from the video. So here they are. Okay, so let's kind of move this somewhere else. Okay, so this is the coordinate system. Let's use a different color. So this is the body fixed coordinate system in the beginning, and here it is at various times in the motion of the body. Okay. And it's as you can see, the orientation of the body fixed coordinate system. Remember this phrase, BFCS, body fixed coordinate system. So the orientation of this is changing with time, and that's the topic over here, orientation. So it's not a fixed orientation, the orientation changes with time. So ultimately we have to graduate from studying simply orientation at a given time to describing how orientation changes with time. Okay, so let's use the green color, how orientation changes with time. Okay, and so that's the main question here, is how to systematically relate two different orientations of a rigid body. Okay, let's begin with that question. Before we can study the orientation changing with time, can we relate this orientation of the rigid body to that orientation? Can we relate this orientation to its orientation at time t equal to 0? So this is time t equal to 0. This is time t1, t2, t3. So how can we relate any of these times? How can we relate these two, these two, these two? Okay, so that's the question for today's lecture. And well, actually we already have the answer. We studied something called the Euler's theorem, right? I think you remember this, Euler's theorem, which said that any two orientation, it should be orientations of a rigid body, are related by a rotation tensor. We saw that at the end of previous lecture, lecture 5, and we proved this theorem by drawing this body fixed coordinate system and looking at its orientation. So we said that the orientation of the rigid body is actually the same as the orientation of the body fixed coordinate system. Okay, so that was lecture 5, and you should go back and remind yourself of that. So that's how we proved Euler's theorem. So this question of how to systematically relate two different orientations of a rigid body reduces to how to represent a rotation tensor, because if we can represent a rotation tensor, then we can represent systematically the orientation of a rigid body and thereby relate it to any other orientation. Okay, so that's how we are going to do this. So let's move on. So the first representation of a rotation tensor, call it R, is given by the so-called axis angle formula. So what is that? So back in lecture 4 we learned that a rotation tensor rotates objects about its real principal axis. So let me remind you. So first of all, I will recall that R has three principal values. One of them is real and plus 1, and the other two, lambda 1 and 2, are a plus minus ib. So that's what we had learned. And corresponding to this, we had a principal vector E3, so that R operating on E3 gave you E3 back. So R did not change E3 at all. And then from this we were able to understand a lot about what R does in terms of its action on objects, which I will now remind you through this figure. So in this figure I have drawn E3, which is the real principal vector, the real principal axis. I have called it axis here, same as real principal vector. I could just as well have written this to be vector. Okay, and so that's E3, and here is any object, in this case a vector A. Let me use vector A, and what's happening is that when R operates on A, it will simply rotate A about E3 by some amount, and that is because A has two components, one along E3 and one perpendicular to E3 in the so-called invariant plane, and nothing happens to A3 E3 because E3 is the principal axis or the principal vector, but A perp is rotated to some other vector, so that this thing rotates in a cone, and that we displayed by this picture, which I shall put down here. Okay, so that's the picture. Let's kind of move this somewhere, and let's kind of make this a little bit neat. Okay. So there we have it. So R operates on this system, and A3 E3 remains the same. A perp is swung over to some other vector whose length is the same as this vector, but there is an angle by which it rotates around E3, and A goes to R dot A, and basically the length remains the same because it's a rotation tensor, but it swings across by an angle theta. Okay, right? And recall this concept of the invariant plane, which said that any vector which lies in this plane remains in the plane. Okay, all right. So from this picture, it seems like every rotation tensor R basically requires the specification of the principal axis E3 about which it's going to rotate things, and the angle theta, which is the angle by which it will rotate things. Okay, so it seems like every rotation tensor can be represented in terms of an axis and an angle, and that is what leads us to the axis angle representation, which says that any rotation tensor can be represented by an axis and an angle, and this is the formula that we get, and which I will now derive for you. Couple of points here. Here n is the real principal vector of R, which over here we have said is equal to E3. Okay, so I have used a unbiased representation n as opposed to a biased representation E3, because E3 is, it's already numbered. So that's what n is. So this is the same as this representation over here, and capital N is the antisymmetric tensor associated with the vector small n, which, if you remember, has the property that any vector b, the cross product of n with any vector b, is the same as the operation of capital N on b. So what that should remind you is that if in this coordinate system E, if n, the vector n is ni ei, then the tensor n in E would be given by zeros minus n3, n2, 0, minus n1, 0, and it is antisymmetric, so the terms on the lower diagonal are obviously this. So that is what capital N is in terms of small n. So small n will be given, you can compute capital N. So this formula is now clear. Okay, theta is the angle by which rotation takes place about small n.